In space since then?
Sure, yeah, I've been in space 4 times.
Great, congratulations.
Yeah.
Yeah.
So how personally were you in space after a NEMO mission?
Yep.
So what did you think about your experiences in NEMO and your experience?
Yeah,
in
I
space?
think NEMO is very representative of spaceflight with respect to the timelines, the teamwork, the reality that you're actually saturated underwater, so it's not a simulation per se, you're actually doing a real mission. So all of that feels very much like a spaceflight. The pace, the task, the seriousness in which you execute the plan and so forth. So it's great training for spaceflight. And we're able to do things like at NEMO that we're not doing in space yet, like going out and on one of them we weighed out at lunar gravity and executed this whole lunar mission. Here we're doing this asteroid work that, like I said, is years in the future. So it's sort of like a very detailed, high fidelity glimpse into the future. And in that sense, we can do things here for orders of magnitude cheaper and orders of magnitude safer than we would in space. And we can learn from that to make sure that we develop the right systems to go to an asteroid. And when I say the right systems, everybody's got ideas about what you might need there, and half of them aren't even good ideas. And so, we're trying to define what we don't need as well as what we need, so we don't spend our money in excess, because we do have limited budgets. We have to be very smart about the way we approach this.
You mentioned before, when we were talking about the differences in viscosity in the water versus space. How did you personally feel about that? I mean, it wasn't a big deal when you got into space? It was still
So we
much like
train, hundreds of hours in a neutral buoyancy lab, and then you get out in space, and I sort of give the analogy, it's like the difference between running through a muddy field with boots on and ice skating. So when you get out into space, even though you don't weigh anything, you in the suit have 500 pounds of mass. And my motto is you cannot go too slow. If you get that mass going fast and then you put the brakes on with your hands, you'll go tumbling out of control. And so, and you can't do that underwater. You can't learn that. So we actually have what we call translation adaptation. So for the first 10 minutes of a spacewalk, you're actually getting your space leg, so to speak, to get the gain set and so forth. So it's like you can't go too slow. Never let your hands get moving faster than your brain. Spacewalks are very mentally demanding because you're thinking about what you're doing now, what your buddy's doing, what's next, where the airlock is, your path back to the airlock, your buddy's path back to the airlock. So your mind is in high gear. It's moving as fast as it can, but your body is moving very slow and deliberate with respect to all the actions that we take. And then the other big difference, underwater, it's a more sensual experience. You can feel the water, you have fish, you have all these things going on. In space, it's, I always say, I understand the sea. I've been diving since I was a kid, so I know the personality of the sea and how to work in it. I think space, you have to spend years in it to totally get the same understanding, but it's very different. It's very antiseptic. There's no life forms flying around there. There's no drag or viscosity of water. One of the great things about space is you have great visibility. I mean, you can see millions of miles even at night. You have your helmet lights, whereas underwater, frequently you can see nothing. I used to be a professional oil field diver, and half the dives you do are down in the mud where you're doing everything by feel and sort of imagining things with your brain. So it's nice to have that visibility.
Just so I'm clear, I like to think mostly like the muddy field with boots. That's underwater.
Yeah.
And the ice skating is space.
Right. Right. So the dynamics are like you're running through a field with muddy boots versus ice skating. It's very different.
And I can see where you could get out of control pretty quickly.
But after, if you have reasonable athletic ability, you quickly understand those gains and get to where you can do whatever you want. But you just have to go slow. And you have to think about, if I'm turning the corner here, where are my feet? I always try to actually stay low and close to the handhold so that the difference between my center of gravity and the application of the force is minimized, so I don't get big moments working on me. If you get your feet up and you're going fast, you come around a corner, you're going to have some inertial effects that you don't want. So you have to think about all of that. But after about 30 minutes, you pretty much have your legs together, and then I've done 4 spacewalks, and it's just very natural after you've done a few of them.
Can I ask what you did on those walks?
Let's see. So the first one we were doing, evaluating all of the techniques that we would use to build and maintain the space station. And the other interesting part of that one was, and so that was all the different ORUs, the different tools, the different interfaces, different restraint systems. The other thing we evaluated on that was these glove heaters, because people had gotten really cold hands, and this is a really special thing that I didn't realize at the time, but for 20 minutes, one of my tasks was to go up on the end of the robot arm, high above the payload bay at night with all the lights off, to see if I would get cold from these glove heaters. And normally lights are on, but I don't think anyone's ever made a spacewalk with no lights on. And I remember in the middle of the night, I was on the end of the robot arm, and I could see Jupiter and its 4 moons with my naked eye.
Wow.
And you could see the Milky Way like 1,000 times brighter than you see in the middle of the ocean in a sailboat. And I remember looking down, I could see a fine line of white light on the wing of the shuttle, and then this crescent of blue as the Earth was rising. And then for about 20 seconds, you're hanging there in the terminator, which is the line between day and night. So you're going from night into day, but for like 20 seconds, you're in this sort of gray, blue environment where the blue of the ocean just permeates out into space, and you're hanging there between day and night. And then we came out on the day side, after doing 45 minutes at night. I remember looking down, and we were over Hurricane Maryland that was over St. Thomas, where I used to teach scuba diving, and I was really overcome with a sense of pride, not for myself, but for this great team at NASA that had the technology and humankind to put me up there above a hurricane. Because I've been through hurricanes, down on the islands, and it's like, this is not good. And here you are, you feel like you're a weather satellite, so you're just looking down. It's amazing that we had the teamwork and the technology to put me up there to see that.
That was coincidence, or that was?
It was coincidence.
Oh, okay, yeah.
Pure coincidence. So on my other spacewalks, we actually installed the airlock on the space station. And then I also am the principal investigator of our decompression research program. And I don't know if you knew this or not, but we actually have to decompress in order to work in a spacesuit, or we'll get the bends.
Oh, really? Okay.
So we're actually saturated at 1 atmosphere in the space station, and we go to 4.3 pounds per square inch in the suit, because we want the delta pressure across the suit to be minimized to improve our mobility and dexterity. So we have to denitrogenate in order to safely make that pressure transition without getting decompression sickness.
Wow.
And on the space shuttle, we had 2 procedures that we used. One was a 4-hour oxygen pre-breathe to get rid of the nitrogen. The other was a staged procedure where we dropped the pressure of the shuttle to 10.2 psi, enriched the breathing mix to 26.5% oxygen, and stayed there for 24 plus hours. And then we only had to do a 40-minute pre-breathe to go out the door. But as we started the space station is huge, and it never comes back to Earth, so we couldn't afford the logistics to lower the pressure of the space station to 10.2 psi. So our baseline plan was to camp out in the airlock overnight at 10.2 psi with no food or bathroom or anything, and then in the morning to get up and put on an oxygen mask, repress to 14.7, skirt out into the space station, use the bathroom, grab some chow, get back in the airlock, come up to 10.2 psi, come off your mask, eat your breakfast, get in your suit. So none of that was very attractive, and so I led a team that developed this exercise pre-brief protocol where we actually do 10 minutes of vigorous exercise at 75% of your max aerobic capacity. The exercise increases your cardiac output and your blood flow, enhances nitrogen elimination. And so we actually did that test. It was a multi-center effort with NASA, the Duke team, Dick Van, Neil Pollack at Duke, and then Ron Nishi at VRDC in Canada, and then Carolyn Fife and Bruce Butler at UT Herman. So we did all these trials, we developed this procedure that had no DCS, and I actually used that on the first spacewalk from the space station. So that was very rewarding to work through all the science of that and then have the opportunity to use it for the first time.
That's fascinating. Could I go back just one more thing that fascinated me too is when you mentioned lunar gravity.
Mhm.
Are you weighting the astronauts when they're out of the Aquarius very, very precisely?
Yes.
So, for instance, when we saw them on Sunday, they were working on an asteroid.
Right.
Would it have been lighter than lunar gravity?
No, asteroid is basically microgravity, so they don't weigh anything. But we did a mission in 2010 where we had the whole lunar lander and all this, and we had a very detailed weigh-out procedure where we weighed them out to have the same ground reaction force they would have on the moon in a suit. And so you're hopping around, and actually lunar gravity is a real sweet spot because it's sort of, you've got enough ground reaction force that you can do tasks, but you can also hop
Yeah.
and you can basically dive through hatches.
Oh,
So
man.
it's sort of like the sweet spot between microgravity.
It's not going to send you tumbling, like,
It's not going to send you
but
tumbling.
enough that you could push
Enough
it. Yeah.
You can dive through a hatch very
Wow.
elegantly.
Slam dunk it from the foul line.
Exactly. And then, in microgravity, every tool we have is tethered.
Yeah.
Because if you drop it, it's gone. On the lunar surface, you don't need that. If you drop it, it's going to land there. You can pick it up. So the lunar gravity is really a real sweet spot. We actually also looked at Mars gravity, and Mars is much higher gravitational force, and that starts getting pretty heavy. So these suits and all that, you start getting really high metabolic rates to work on Mars with the kinds of suits that we use now. So lunar is the real sweet spot. And an asteroid, in some ways, is like the worst combination of the dirt of the moon, but no ground reaction force. And on space station, we've engineered all these translation paths and handholds and foot restraints and body restraints. On an asteroid, you have no control over it. And so we've had to develop these techniques using the translation lines or the space exploration vehicles and subs and foot restraints as a way to effectively translate and restrain yourself while you're doing these tasks in this dirty environment like the moon, but with no ground reaction force to help you out.
This is, I really appreciate your time.
Yeah.
Yeah, sweet.
I
two quick, or hopefully quick. What's the spacewalk like in diving? The position's horizontal that you cruise along. You know, with spacewalk, are you what's the position? Are you vertical? Or are you trying to fly like
it's
that?
all relative to the surface, right? So what you saw with the subs down there, we would be doing that exact same orientation relative to an asteroid. So in some cases, we would be vertical in the first restraints if you're working against a sheer cliff or something.
Okay,
in other cases, you'd be more prone, reaching in front of you the way you saw us working.
Okay. I actually didn't see that part, but yeah. So it's just whatever you need.
The geometry or the surface topography calls for.
Okay. And then, is there? Sorry, I don't know these answers. In space, is there spots of space that are completely still, and there are spots that have kind of like current or something like that?
No, because there's a few molecules running around out in space, but nothing that you can even measure in terms of a pressure. And so there's not any current. It's a vacuum.
Okay.
So there's nothing.
Yeah, I didn't know if close to something close to an asteroid belt or something like that. If that's causing some kind of little mini tornado of some sort?
No, you
I'm going
wouldn't.
to run and check on the group that's still at NOAA. If y'all need me, I'll be right back, okay?
And then you just come get me when you need
Yeah,
me?
we'll switch them out.
Okay. So no, there's absolutely no aerodynamic forces or
Okay.
hydrodynamic forces, anything like that. You do have the gravitational forces, and so as you go
Oh.
around this asteroid, even though it is so small that it doesn't have a lot of gravity, and as a human you probably can't sense it, but it does affect the way your vehicle moves.
Right. So all of a sudden you'll be moving at one pace, and you're staying that your foot's in the same the same place on the pedal.
Right.
But all of a sudden, as you get close, like you might feel like a surge of something
No,
like that.
Not quite like that. So, depending on where the spin axis is, as you go out from that spin axis, your tangential velocity increases. And also, these things are not uniform, so there could be pockets of higher gravity than others. And so, as you get out, then the rate that you have to fly the vehicle to match the asteroid's spin rate increases. So, I'll try to give a simple example. So if I started out working right at the spin axis, it's really easy to maintain station because it's not spinning around. But then if I did a 500-foot translation, and then I went to go to work, that asteroid's going to be moving away from me. So I have to put rates on the vehicle to match the movement of that tangential velocity at that distance from the spin axis.
Okay. All right. It helps. Yeah.
Yeah.